Let's continue our discussion of the synthesis of amines by looking at the preparation of amines by reductive methods. There are actually two of these methods that we've already discussed: the reduction of a nitrile to a primary amine, and the reduction of a nitro group to an aryl amine. Nitro groups can be reduced in the presence of ketones and aldehydes with tin chloride and HCl followed by sodium hydroxide to form aryl amines. When nitriles are reduced with lithium aluminum hydride followed by workup, they give primary amines bound to primary carbons. A more versatile method of the preparation of amines is the reductive amination of ketones and aldehydes. For example, let's take this generic ketone here and say I treat it with ammonia in the presence of an acid. Under these conditions, what we'd expect is that we would form an imine. Imines can be easily reduced by hydrogenation to amines. Lots of other reducing agents can do this reaction as well. A very common one is sodium cyanoborohydride. This is sodium borohydride where one of the hydrogen atoms has been replaced with a cyanide. Since the cyanide group is electron withdrawing, it reduces the reactivity of the boron-hydrogen bond, meaning that an imine can be reduced, but a ketone or an aldehyde cannot be reduced. This reagent allows for so-called one-pot reactions, where the amine, the ketone or aldehyde, a proton catalyst, and the reducing agent are combined all in the same pot all at the same time. This will give very structurally diverse amines. We can prepare primary, secondary, or tertiary amines, and we can prepare them at methyl primary or secondary carbons. For example, let's say we wanted to prepare methamphetamine. If we wanted to make this by reductive amination, there are two carbon-nitrogen bonds, so there are two possible methods we could use to form it. One method focusing on this bond would combine phenylacetone with methylamine. The other would combine phenylpropanolamine with formaldehyde. In both cases, the reaction would look similar: ketone plus amine with an acid catalyst and a reducing agent, or amine plus an aldehyde and an acid catalyst and reducing reagent, but the result would be the same in either case. What you may have noticed is that the synthetic methods we've discussed so far have a gap. None of them are able to prepare amines at tertiary carbons, like for instance terbutylamine. Think about the methods we've discussed so far and figure out why we can't make this via any of our other methods. There is a method that exists in order to prepare this, which is known as the Ritter reaction. The Ritter reaction starts with a tertiary alcohol, like terbutanol, and treats it with hydrogen cyanide in the presence of sulfuric acid. This will give a formamide, which can be hydrolyzed with water and potassium hydroxide to release the amine. It would be good mechanistic practice to show a mechanism for this reaction. Show the mechanism, then come back and we'll discuss how this reaction works. Rather than stepping through the whole mechanism, I'm going to show parts of it so that you can check your work. The first part of the mechanism involves protonation of the OH group and loss of water to form a carbocation. This carbocation can then react with nucleophiles like the nitrogen of hydrogen cyanide. This produces a protonated isonitrile, which can be hydrolyzed under acidic conditions via the mechanism that we discussed back in Chapter 20. Practice these methods. Use reductive amination to synthesize these three appetite suppressants. This first one is phentermine, which was present in the now banned appetite suppressant called fen-phen, banned due to its propensity to cause heart attacks. This one is diethylpropion, which is known by the brand name ampheprinone. And finally, clobenzarex, which are known as greenies by baseball players that use them illegally for performance-enhancing purposes. For these syntheses, you may start with any substance containing carbon, oxygen, or halogens. Use ammonia, sodium azide, or sodium cyanide as your only source of nitrogen atoms. You may use any other reagents as necessary. Take a moment to work through these syntheses, and then we'll discuss the methods together. Let's start with phentermine. As this is an amine bound to a tertiary carbon, the only way we have to synthesize this is via the Ritter reaction. We would want to start with this tertiary alcohol, treat it with sodium cyanide in the presence of an acid to generate hydrogen cyanide in situ to get this formamide. The formamide would then be hydrolyzed to release the amine. Ampheprinone is slightly different due to the presence of different groups bound to the nitrogen, but we could recognize this bond as being formed from an alpha haloketone, which we could prepare by halogenation, and diethylamine. Diethylamine can be formed by two successive reductive amination reactions. Note that we could not prepare it by alkylation due to the fact that alkylation can either put one alkyl group on or four alkyl groups on, but not two or three. So we would start with this 2-carbon aldehyde, perform reductive amination to get ethylamine, do a second round to produce diethylamine, then add diethylamine with our alpha haloketone to get our product. Take a look at both of these and try to figure out if there are any other routes that could possibly work to prepare them. Try these again. In the case of clobenzarex, we have a much more complicated set of routes that we could put together. There's lots of potential right answers here. For instance, on this side of the nitrogen we have a primary carbon, which means that could be derived from an amide, an azide, an aldehyde, or reductive amination. Over here we have a secondary carbon, which means that we are restricted to using only reductive amination. There are lots of possible routes. What I'm going to do here is I'm going to walk through some of the retrosynthetic analysis that we would do, and then I'm going to leave it to you to put these together in a forward direction to finish the syntheses. Let's start by taking a look at the bond of the secondary carbon. Since this could only be formed by reductive amination, that means that it must have come from a ketone and this primary amine. If we look at the bond on the other side, we could also assume that that one is formed by reductive amination. That bond could also have been formed from an amide, which would mean that our starting materials were acid chlorides and amines. Notice that two of these routes, the orange arrow and the blue arrow, both have phenylpropylamine as their source of nitrogen atoms. So if we look at the synthesis of this, we have a nitrogen and a secondary carbon, meaning that we could either be looking at displacement of halide by sodium azide followed by reduction, or reductive amination with ammonia. Going back up to the benzylamine, this could either be formed similarly from reductive amination of an aldehyde or displacement of a chloride by sodium azide. Work these forward and then try to figure out if there's anything that I've left out. Are there other routes that would work? If we modified the starting restrictions, are there other starting materials that you could have started with to prepare these same amines? This is excellent practice for the end of the chapter. Finally, we'll wrap up with the discussion of using a nitrogen atom as a good leaving group in several interesting synthetic reactions.